In 2023, the United States Geological Survey estimated that China accounted for roughly 70% of global rare earth mine production, but close to 90% of global rare earth processing capacity. The mines are scattered across continents. The chemistry is not. That imbalance is not geological, it is infrastructural. And infrastructure, once embedded, becomes power. Rare earth elements are rarely rare in the ground. They exist in the United States, Australia, Africa, and parts of Europe. The constraint is not discovery, it is transformation. Ores extracted from a mine are chemically complex mixtures. They must be separated through solvent extraction, refined into oxides, converted into metals, alloyed, and then manufactured into high-performance magnets. Each of those steps is capital intensive. Each step generates chemical waste. Each step requires engineering expertise accumulated through repetition. The leverage lies in the repetition. China did not dominate rare earth processing because it possessed a monopoly on geology. It dominated because it accepted the economic and environmental burden of refining when others did not. During the 1980s and 1990s, as prices fell and environmental standards tightened in Western economies, processing capacity shut down. Facilities in the United States and Europe became uncompetitive. The margins were thin. The waste was politically costly. China absorbed the volatility. Provincial governments tolerated pollution. State banks extended long-duration credit. Consolidation followed. Small operators were merged into large state-backed entities. Licensing regimes tightened. Environmental inspections reduced illegal mining, but reinforced central control. Over time, mining, separation, refining, and magnet production were integrated into coordinated industrial groups. Rare earth policy was not isolated. It was linked to electric vehicle strategy, renewable energy expansion, robotics, and defense modernization. The system became self-reinforcing. Once processing clusters form, magnet manufacturers co-locate. Skilled chemists train younger engineers. Equipment suppliers specialize in separation columns and high-purity reagents. Logistics networks optimize around predictable flows. Costs fall not only because of labor, but because of ecosystem density. This density is difficult to replicate. A mine can be reopened within years. A processing ecosystem takes decades. That distinction matters because rare earth elements are not marginal inputs. Neodymium and praseodymium magnets power electric vehicle motors. Dysprosium improves high-temperature performance in wind turbines. Samarium cobalt magnets are used in precision-guided defense systems and advanced aerospace components. In an F-35 fighter jet, small quantities of rare earth materials are embedded across avionics, radar, and control systems. In offshore wind turbines, permanent magnets reduce maintenance and improve efficiency. In electric vehicles, magnet motors allow lighter, more energy-dense designs. The quantities per unit are small. The systemic dependence is not. The leverage does not require a full export ban. It operates through modulation, export licensing reviews, environmental inspections, quota adjustments, administrative pacing. The 2010 dispute with Japan illustrated the sensitivity. Export flows tightened during a diplomatic disagreement, and global prices surged dramatically. Although trade eventually normalized and legal rulings followed, the episode revealed how quickly markets react to perceived constraint. Price spikes alone can reshape supply chains. When rare earth prices rise sharply, downstream manufacturers face margin compression. Automakers adjust sourcing strategies. Defense procurement budgets stretch. Renewable energy projects recalculate cost curves. Volatility becomes influence. What makes this structure particularly durable is pricing asymmetry. Rare earth markets are relatively small compared to oil or copper. Sudden supply adjustments can move prices significantly. Yet if alternative processors begin entering the market, oversupply can push prices down again, undermining new investments. This boom-bust cycle discourages competitors. Investors hesitate to finance multi-billion-dollar separation facilities if price collapses can render them unprofitable within years. Thus, volatility becomes a structural defense mechanism. Western economies are attempting to respond. The United States has supported expansion at Mountain Pass and downstream facilities in Texas. Australia's Lynas has developed processing outside China and is partnering with the US Department of Defense. The European Union has introduced critical raw materials legislation aimed at reducing external dependency. Yet replication faces constraints. Environmental permitting in advanced economies can take years. Community opposition to chemical processing plants slows development. Skilled labor pools must be trained. Long-term feedstock contracts must be secured. Waste disposal systems must comply with strict regulatory standards. Even when plants are built, scale matters. A single facility processing a fraction of global demand does not neutralize systemic concentration. Moreover, coordination differs. In China, rare earth processing aligns with national electric vehicle targets, battery development, and wind turbine manufacturing. Domestic demand reinforces domestic supply. The magnet produced feeds directly into nationally prioritized industries. In decentralized market systems, mining firms, processors, automakers, and defense contractors operate under separate financial incentives. Governments may subsidize, but rarely consolidate. Alignment emerges slowly. The difference is architectural, not ideological. There is also a geopolitical dimension that remains understated in most public discussions. Rare earth processing intersects with semiconductor restrictions, battery supply chains, and broader trade policy tensions. When export controls expand in one sector, responses may emerge in another. The interdependence is layered. Consider the capital markets dimension. Multinational manufacturers now factor mineral concentration risk into long-term planning. Insurance costs reflect geopolitical uncertainty. Equity valuations incorporate supply chain resilience metrics. ESG considerations intersect with processing location, given environmental sensitivities. A choke point does not only influence material flow, it influences capital allocation. Looking forward, 3 structural paths are possible. The first is gradual diversification. New processing hubs in North America, Australia, and Europe expand steadily over the next decade. Market share becomes less concentrated, though China remains dominant. This scenario requires sustained political support, patient capital, and tolerance for higher costs. The second is accelerated decoupling triggered by external shocks. A geopolitical escalation or severe trade rupture could force rapid policy action. Governments may subsidize emergency capacity buildouts. Prices could spike sharply. Short-term dislocation would precede long-term rebalancing. The third is continued concentration through competitive pressure. If alternative facilities struggle financially due to price swings, expansion could stall. China's incumbency advantage would persist, reinforced by ecosystem density and cost efficiency. Which path prevails depends less on geology than on policy coordination and capital discipline. There is also a subtle strategic question. Does leverage require activation to be effective, or is the existence of concentration sufficient to shape behavior? In many cases, the knowledge of dependency alters negotiation dynamics without overt action. Companies diversify suppliers preemptively. Governments negotiate trade frameworks cautiously. Strategic stockpiles are accumulated quietly. Leverage often operates in anticipation, not execution. Meanwhile, global demand continues rising. The International Energy Agency projects that mineral demand for clean energy technologies could multiply several times under net zero pathways. Electric vehicles require more mineral inputs than conventional vehicles. Wind turbines scale in size and magnet intensity. As electrification accelerates, rare earth intensity across advanced manufacturing increases. The green transition reduces dependence on hydrocarbons, but introduces dependence on mineral processing networks. This is not an anomaly of one country. It reflects a broader pattern of industrial power. In the 19th century, Britain controlled textile transformation, even when cotton was grown abroad. In the late 20th century, Japan dominated advanced materials critical for semiconductor fabrication. In both cases, influence rested in the middle of the chain. Transformation nodes shape outcomes. Rare earth processing is one such node. Over decades, China constructed not only factories, but institutions. Export licensing systems, state-backed consolidation, environmental oversight mechanisms, integration with 5-year plans, coordination with electric vehicle manufacturers and wind turbine producers. Infrastructure becomes inertia. Can it be reversed? Yes, over time. But time itself is the scarce resource. Building alternative capacity requires years. Developing workforce expertise requires cycles of training. Aligning private capital with public policy requires political stability. And throughout this period, demand continues climbing. Resilience is not built overnight, it is layered. The rare earth story, therefore, extends beyond minerals. It illustrates how industrial ecosystems create structural options. Once embedded, they constrain the speed at which others can respond. The mines may be global, the deposits may be widely distributed, but until processing capacity becomes similarly diffuse, the center of gravity remains where the chemistry happens. In modern supply chains, power rarely announces itself dramatically. It resides in industrial clusters, in separation columns, in licensing systems, in quiet inspections. It is exercised not through constant confrontation, but through the awareness that modulation is possible. And as the world moves deeper into electrification, automation, and advanced manufacturing, the quiet valves of rare earth processing will continue to regulate the flow, shaping prices, shaping strategy, shaping timelines, often invisibly. Geology begins the story, infrastructure decides how it ends.